Alright, lesson 2 in chapter 1 is going to be over speed and velocity. Those are two different things. It's going to be important to remember that. Vocab: speed is a measure of the distance an object travels per unit of time. That unit of time piece is going to be very important. Constant speed is the rate of change of position in which the same distance is traveled each second or each unit of time. A second is a unit of time. 10 seconds could be a unit of time, just so that you're consistent with what that is. Instantaneous speed is a speed at specific instant in time. Average speed is the total distance traveled divided by the total time taken to travel that distance. And velocity is the speed and the direction of a moving object. So, to calculate speed, you divide the distance traveled by the time it takes to go that distance. We've worked with some conversions already, so we could say 5 meters per second, right? In this case, our distance traveled would be 5 meters, and the time to do that would be 1 second per 1 second. The same thing would go for if you were saying 10 meters per 2 seconds. That's just not simplified, like 5 per 1 second. So 10 meters per 2 second is going to mean that we're traveling 10 meters every 2 seconds. The units of speed, or the unit of speed, are units of distance divided by the unit of time. So it's meters per second, feet per second, miles per hour, things like that. Those are all units for speed. For the SI, it will be meters per second. Constant speed is when you cover the same distance per time. So if we look over here at our constant speed, which is labeled x, notice the distance between the dots are the same for constant speed. So we should be the same distance across for all of those dots. That means that we're traveling the same distance per unit time. This would be like a car that's driving in a straight line and doesn't have to brake on the highway. We also have increasing speed, where the distance between each dot gets longer. That means we're covering more time more distance per the same unit of time. And decreasing speed means that we're covering less distance per unit of time as we go on. Changing speed. We know that cars rarely go to constant speed. More often, the speed is changing, braking, accelerating, things like that. The speedometer is a measurement of instantaneous speed. It tells us the speed the car is currently going at that exact moment. Average speed. Describing the car's speed is easy if the speed is constant. But what if it's changing? What if the speed of the car, like we know, is changing? We're braking, we're accelerating, things like that. If the car is speeding up and slowing down, we can find the average speed. We find that by dividing the distance that's been traveled by the time it took to travel that distance. So here's our formula for average speed. Velocity is the term we're going to use. So velocity, v, equals d, which is distance, divided by t, which is time. So average speed, or velocity, is equal to distance divided by time. Again, the unit here is meters per second. So average speed practice. Melissa shot a model rocket 360 meters into the air. It took the rocket 4 seconds to fly that far. What is the average speed of the rocket? First thing you need to do is you need to find out what you know. We know that the distance, in this case, is 360 meters. We also know that the time is 4 seconds. What are we looking for? We're looking for velocity, or v. What's our formula? V equals d over t. Next, after we know all that stuff, we can use our numbers that we have and our formula that we're given and plug in the values that we know. So we know that d equals 360 and t equals 4. So v is equal to 360 meters over 4 seconds. If we divide 360 by 4, you're left with, our units don't cross out here, so we have meters over seconds. We're left with, the velocity is 90 meters per second. Distance and time graphs, it's going to be important that you know how to read these. Time will always be on your x-axis, right? This is our x-axis down here. And distance will be on the y-axis. So for our first line, let's use this as our first line. It says fast, steady speed. So what you're looking at is if time's on our x and distance is on our y, we're traveling a lot of distance, so we're going up really high on the y-axis and not very much time on the x-axis. So that means we're going fast. We're going really far in a short amount of time, so we have to be going really fast to do that. Here we have this curved one. This says it's something that's getting faster. We start by not covering very much distance. Remember that up and down is distance. We don't have very much distance. We haven't gone up and down very much. And by the end of it, we're going up and down a lot more. So that means we must be going faster. We also have this tabletop looking line. So here we have a steady increase in speed, or not an increase, but a steady speed where we're covering some ground, or we're covering some distance, right? Up and down is distance, and across is time. So we're covering some distance in the amount of time. When it tables off like this, when it's just straight across, that means it's stationary, right? Because if it's not moving up or down, it's stationary. So it'd be like we drove the bus to a certain point, we stopped the bus, and we sat there for most of the day, and then when it starts to come back down, it's returning to start. So it's decreasing its distance, so it's coming back. Alright, so we used velocity already once to describe one of our formulas. Now we're going to talk about what velocity really means. Describing speed does not completely describe motion. You also need to include the direction. Velocity takes both of these things into account. Velocity is represented by an arrow. The larger the arrow means greater speed. So over here on our example, we have that this man is walking 5 kilometers per hour. If he was walking 10 kilometers per hour, we would double the size of this arrow so that we would know he was walking faster. You're going to see arrows a lot in the upcoming chapters. We use it for velocity, acceleration, force, and the bigger the arrow always means the greater the value. In the picture, both the man and the woman have the same speed, right? It says 5 kilometers per hour and 5 kilometers per hour. However, they have different velocities because they are moving in different directions. So the speed's equal, but this man has a velocity of 5 kilometers per hour east, and the woman has a velocity of 5 kilometers per hour west. So they're different velocities that have the same speed. Changes in velocity. The changes in the arrows represent a change in velocity. Here we can assume that this is a bouncy ball that we've bounced. We're going to have two measurements here when we're looking at the bouncy ball. We have a velocity y, which is saying up and down, velocity up and down. So here we're traveling up, and that's why this arrow is so big here, because we're really traveling up pretty quickly. Here we have velocity x, which is our going across motion. You'll notice that the x doesn't change very much because we're going across at about the same speed. But our y arrow changes with each individual picture. So as we get to the top, if you've ever bounced a ball before, and I'm imagining that you have, you'll notice that it gets to a certain spot, and then it stops going up, and it starts coming down. So each of these has a change in velocity. That's why we draw that v sub y, or the vy there, with a smaller and smaller arrow, and then it gets to the top, and it actually reverses and has an arrow going down. It gets bigger and bigger. Velocity changes when speed changes, when the direction changes, or when both change. So here we have speed changing for all of these, and then here we actually have a directional change. So it's going from up to down. Here it's slowing down, going up, slowing down, going up, slowing down, going up. It stopped going up. Now it's coming down, coming down, coming down. The ball is changing velocities the entire time. As it slows to a stop at the top, then begins to fall again. And that's what we were talking about. That will do it for lesson number 2.